Okay, thank you and welcome. Good to see you again. I appreciate your time. I know you're busy, but today I think we have some important news and some great technology innovations that I think you'll be interested in. So thank you. Okay, just a reminder about Altera. We have a new set of products we call Generation 10, and there are 3 products. Max 10, single integrated flash FPGA, single chip, TSMC manufactured. Aria 10, leading edge mid-range product with integrated ARM processor, TSMC 20 nanometer process. Both of these products shipping today, and today we'll talk about Stratix 10, and we're introducing the product details about Stratix 10. And this product is built on Intel process technology. Okay. So as you can see, we have current products today that are built both on TSMC and Intel. Both are very strong partnerships. Okay, so I wanted to lead off just with an explanation of Stratix 10. And we have announced the Stratix 10 name before, so maybe it doesn't sound like new news to you, but we haven't disclosed some of the important details about the product. And that's what I will do today. Maybe explain. And there are 3 important capabilities that we're disclosing the details in our announcement. One is, how do we achieve 2x core performance, or 1 gigahertz FPGA? First time in the industry. Another is 3D SIP, or system in package. So this is multi-die or multi-chip in a single package. And the third is some new security capabilities for FPGAs. So those are the 3 big areas I'll focus on today. So let me start off with the first topic, and that's 2x performance, or double the performance of current FPGAs with a new architecture we call HyperFlex. And first, let me try to explain simply what the problem is with increasing performance in FPGAs today. And the problem can be best summarized by the size of this green box here. And the green box shows that in a logic design, in a design built in an FPGA, the problem in performance is the size of the routing delay. The delay through the logic or the function is actually quite fast. But as process technology gets more advanced, the routing delay, due to the resistance in the wires getting very low, has not improved as much as the logic delay. So this problem with the routing delay not getting better is limiting the performance of FPGAs. And one of the ways that FPGA vendors, Xilinx, Altera, really everybody, have tried to solve the green box problem is by a wider bus or a wider pipe, right? Because system performance is all about getting data through the chip from one side to the other as fast as possible. So to get more data, we've tried to make the bus or the pipe bigger to push more data through. But the problem is, of course, when you make the pipe or the bus bigger, it creates congestion, lots of resources required for a bigger bus, which makes the green box even bigger. So our customers have a big challenge, and we have a big challenge as the buses get too wide. We need to make them smaller and solve the bandwidth problem by making the chip faster. So smaller pipe, faster going through is a better solution. It solves this green box problem. So again, just to summarize, by doubling the performance, and I'll explain, we take the green box from a problem to something we can manage and achieve high performance. So if you'll bear with me, I'll show a little bit of detail, a little bit of technical detail to try to help explain this. So maybe you're familiar with this. I don't know. I'll go quickly through this. But fundamentally, the challenge for customers and engineers is trying to make the longest path or the longest delay from one function to another function as short as possible. So this is nanoseconds, which is, of course, a measure of time. And the longer this time, the less the performance. So the challenge is to try to reduce this number. And here's the innovation. So here's what Altera did in Stratix 10. We took registers, storage components to hold a bit, flip-flops. Some of you are probably very familiar. Typically that's in the function block where the function gets done. We've taken that register and we've put it everywhere in the routing, in the fabric. So we say ubiquitous in the US, or everywhere. Millions of, we say hyper marketing, hyper registers, but millions of registers all through the fabric. And I'll explain why that matters. So once we do that, I go back to this picture. What we can do is we can fix or improve this 3.5 number. And we do that by ensuring the longest path is shorter. So instead of 3.5, we have 1.2 plus 1.1 plus 1.2. Still 3.5, but the path from one resource to the next is shorter. So now the 1.2 determines the performance, and your performance goes up dramatically. I'll use a brief analogy to explain it as well, for those of you not familiar with the concept, but maybe go ahead. One way to think of it, and maybe you're very familiar with this, is think about this as the Incheon Bridge, a large bridge. But say the bridge can only hold one car. Then you have to, if you have 100 cars trying to get over the bridge, you have 99 cars waiting while one car finishes. Here, we break the bridge into 3 smaller bridges. So you can have multiple cars going over at the same time, and you get more cars through in the same period of time. Maybe it's a very common concept for you. It's a very simple but powerful concept to get double the performance or more. And in engineering school, we learn this as retiming or pipelining, very common ASIC, FPGA logic design practice. So it's not a new idea in engineering, but it's a new architecture that implements that idea more efficiently. So HyperFlex, so this architecture is only in Stratix 10, no other Altera product, and not available from any other FPGA. Okay, so let me spend 3 slides on why it matters. And let me tell you, today we have over 100 customers using our early evaluation software. The software allows them to use the HyperFlex approach and evaluate their performance improvement. And when our customers have done that in multiple applications, our customers' result, so their design, shows very big improvement over traditional architecture. The other is power. So this may sound strange, or we say counterintuitive, or may not make sense, but with 2x performance, we reduce power. So usually power goes up with higher performance. The reason we get savings is because we're making that pipe smaller. So we're using less resources. So for example, in very high-end OTN, or optical transport networking, there's a need to deploy 400 gigabits per second systems. In traditional architecture, it's 1,000 bits wide pipe. With HyperFlex, we can cut that in half by, again, doubling the frequency, the speed. So when you cut the pipe in half, you save a lot of power. Now, I'll say there are other benefits in Stratix 10 that help this. The Intel process, and also some ways that we control the voltage ID, that I'll talk about later. But HyperFlex is a big reason. So let me give 2 examples in a little bit more detail. One is data center. So data center application. This is today. We use Stratix 5, but Xilinx UltraScale, similar. And this is new, innovative HyperFlex architecture. So the problem the data center customers are trying to solve is very fast lookup, or very fast search, or offloading Xeon for application acceleration, computational acceleration. To do that, to achieve what they really want to achieve, requires many FPGAs today. And the performance of today's architecture, because of the wide pipe, is constrained or limited. In Stratix 10, because of higher density and because of performance improvement, we can go from 5 to single FPGA. And of course, when you do that, you save a lot of power, and you're able to meet the throughput or the acceleration required by the Xeon processor or the Intel processor. So a good solution for the data center. So let me show another example in wireline, we say, or optical networking, communicating data across very long distances requiring optics. Today, single FPGA, almost 1 million logic elements, 350 megahertz. To implement the same logic in Stratix 10, we can go to a smaller device. So 650, 900, smaller. So the board area is smaller, the power is lower, because there's less resources, and yet we're able to achieve performance and higher throughput. So this is an example of power savings and area savings by, again, reducing the number of resources required using the new architecture. So that's what I wanted to say about 2x, about HyperFlex, about performance. So a big change in the FPGA technology to enable both very high performance and also very good and low power efficiency. Now I'd like to explain to you our second big piece of news. And that's about the multi-chip or multi-die capability in Stratix 10. This will be the first time Altera does multi-die FPGA, and it'll be the first time in the industry a true heterogeneous, we say heterogeneous or multiple function, multi-die capability is provided. And my third point is it's a very close partnership with Intel on packaging technology, which I'll explain. So let me first spend one slide talking about why do we need multi-die? Why would we even do this? And here's the challenge. The challenge is the data rates in the transceiver or the pin that has to talk at very high speed to other devices. The range of data rates is getting very broad. And this is a very complicated problem to solve in a single chip. So we need a way to solve this problem. Another problem is the standards in the market, many are not ready yet to be hardened in silicon, to be made into an ASIC. For example, Gen 4 PCIe is not done yet. The standard is not done. So we need a solution that allows us to support protocols that are not standards yet. And the third problem is to support these data rates, different modulation schemes are required that add complexity to how you build a chip. So these are Altera's problems in meeting our customers' needs. So here's what we are doing in Stratix 10, and what we're announcing in 2 weeks. So the solution is to create a product that is flexible, scalable, and enables faster introduction of products. And here's what it is. It is a monolithic or single FPGA die. All the fabric in one die. Supported by, we say tile, but it's a die. It's a die. Multiple die that has hard IP, ASIC IP for protocol, and high-speed transceiver. And one of the key benefits here is we can add capability to the tiles by replacing with other capability without creating a large new FPGA die. So that gives us flexibility to add and also scalability to change the number of tiles based upon the cost or the performance need. So I'd like to make a couple more points on this slide. One is the size of this device, the capacity, is up to 5.5 million logic elements, which is 5 times bigger than any device Altera has provided. And we can do that in a monolithic single die because we have a technology called redundancy in the FPGA that gives us high yield. Our competitor and alternatives in the market have to use multiple FPGA die above 1 million, so at very low densities. And this gives us a usability and performance advantage by having all the logic next to each other in a single die. And the last point I'll make on this slide is EMIB. So EMIB means Embedded Multi-Die Interconnect Bridge. It is a Intel word, Intel term. So Altera has partnered closely on a technology level with Intel to integrate 3D silicon, this is silicon chip, in the package to provide the connectivity. And the reason it matters is because this connectivity is much more efficient than silicon interposer, than other solutions use. Because it is a dedicated piece of silicon for the connectivity. It doesn't have the reliability and the cost issues of a large interposer. Okay, so the next point I'd like to talk to you about is security. And I'd like to give you a little more detail than in the press release on security capability in Stratix 10. And what we're doing in Stratix 10 is making the device easier for customers who do cloud, enterprise, hosted capability, military, but even wireline communications. All of these customers have a similar requirement, and that's to treat different parts of their design with different levels of security. And this is a new requirement because users of FPGAs are now integrating more of the system into a single FPGA chip, and they need to treat the different functions separately and secure them independently. Okay, so I have 3 more slides, 3 more points I want to get through, and then maybe we could open for question and answer. One is, I just wanted to remind you, we've talked about before that in all Stratix 10, we have an integrated ARM processing complex or system with quad core, 4 cores of A53 64-bit processor. And one key point here is one, it's a very powerful computing complex. And the second is we provide ARM processing across all of our products, from low end, mid-range to high end. And we have compatibility with today's ARM products to Stratix 10. So the customer reuse is easy and built in. And I think it's always interesting to note, this will be the first time ARM processor on Intel wafer. So some people thought that may never happen, but it will with Stratix 10. Okay, and then many of you may have talked to us, or you may have seen an announcement we made 2 weeks ago about Spectra Q engine. This is new capability in our development tools. And that engine was built with all our products in mind, but in particular Stratix 10. And the reason is to improve productivity, to make it easier to reuse a design, to make it faster to get the design compiled from software to hardware, and to support software developers in creating hardware. So using C language to create a hardware design, which we call high-level synthesis or high-level design tools. And then my final point, you may be aware Altera is more than an FPGA company today. We also have power management products. We call those products Empyrean. And I think with Stratix 10, you're seeing the value of Altera providing power management increasing. And one of the key technologies here is the ability, and maybe you're familiar with the component, the FPGA, to tell the power management device what voltage it needs. And to uniquely do that, to optimize the amount of voltage that goes to the device based upon how it was manufactured. This is something Intel does with almost all their products. Voltage ID. The ability for the processor or the FPGA to say, I need 0.85 volts instead of 0.86 to run at my optimum level. So because of our partnership with Intel, we're able to bring this technology broadly to FPGAs to improve both the power and performance. So thanks for your attention. Let me just briefly summarize. So a couple of big components to our announcement. One is the new architecture with Intel process that provides 2x core performance. One is the multi-die heterogeneous approach, system in package. Another is new security capability. I will just add quickly that these capabilities enable things like 10 teraflops in a single chip, or 80 gigaflops per watt, which gives an order of magnitude, or 10x, better power performance per power capability than a GPU, NVIDIA GPU application, for applications like data center. So where you'll see Stratix 10 in Korea playing more of a level is integrating more of the system, replacing more of the ASIC, and replacing more of the traditional GPU for acceleration type functions. So I spend most of my time with customers. I'm in Asia Pacific region maybe 6 times per year. It's a pleasure to talk to you. Different experience for me. I've been at Altera 4 years. I was at Xilinx for 11 years before that. Yeah. So I've been doing this for over 15 years. And I think this is remarkable from what I've seen. And really opens up new solution for customers and solve new problems. So we're very excited. Thanks for your time. Thank you. Okay.